Hi, today I'm going to share some of my experiences around creating dynamic GraphQL schemas for public GraphQL APIs. I'm Rob Van Genup, and my pronouns are he and him. I'm based in Toronto, Canada, and I've spent the last 3 years working on building GraphQL platforms. I currently work at Shopify as a senior developer focused on API patterns and toolings, and I can be reached on Twitter, LinkedIn, GitHub, and other platforms using the handle RavVanGen, so feel free to reach out and connect anytime. And I have a fun-loving dog named Momo who loves to remind me to take regular breaks from tech. Dynamic schemas can reduce the cognitive load on our users. Let's dig into that statement today by exploring ways we can define the schema, ways we could kind of customize the schema's behavior, perhaps by looking at the execution context to know how our system should behave, and finally, how API versioning can be used to benefit our users. Digging into the defining schemas, there are two kind of approaches that are commonly used or described as. One is Schema First, where we're using the GraphQL schema definition language to describe the GraphQL services type system. This is an interoperable language, agnostic definition language that's kind of consumable by any GraphQL tool, whether it's a client, a server, or some visualization tool, for example, regardless of the language used to implement that tool. It's generally static, where if you want custom behavior, you're generally implementing that through directive behaviors. Here's an example of what a SDL would look like, where we have a file that describes what the schema looks like, the scalars, the interfaces, enumerations, and the type system. So in this case, we have a product, for example, that's implementing the node interface. We have fields like ID, name, description, body, and created at. Specifically of note, the body is deprecated. We're saying, hey, don't use this. You should probably use something newer, more recommended, like description. So this format is rather concise and accessible for non-technical people. There's no conditionals, loops, or complex branching logic. It's all about the shape of the data, how to view and modify it, and the resolvers and the implementation is actually defined separately, likely afterwards in the separate server. On the other hand, we have also CodeFirst, which is still trying to say API design is important and worth considering up front, but we're expressing the implementation through a programming language, first and foremost, where the result of it is an exportable SDL contract. Often there's a close proximity between the type definitions and the resolvers, and we can actually use the programming language's runtime inline to automate portions of the schema definition and hopefully saving some error-prone repetition. In the code-first approach, it's also a lot easier, perhaps, to have some modularization. So you have things like namespaces, inheritance, mix-ins that help kind of separate the concerns and making it kind of out of the box easier to scale for larger projects without involving additional tooling, where we can more easily assign pieces and ownership of functionality to different teams. So in Shopify's case, one of our largest public APIs is the admin API, which currently has over 135,000 lines of code in the SDL file itself. So in that kind of large sense, it's important to divvy up pieces of that to be owned by different teams, and effective schema management is key to that. In this case, we have a GraphQL Ruby example of a definition of a product type for the GraphQL type system. It's important to note that the server is not limited by the schema definition language. We actually have like a superset of functional capabilities provided by the Ruby runtime. We have keywords like implements, where we're indicating that we're implementing a GraphQL interface, which is the relay node definition, and we're conforming to that standard. We have helper functions like global ID field, where we have this helper that automatically and consistently defines what it means to have an ID field on a product type, so that it's returning an ID scalar, it's not nullable, for example. Also, it's quite often the case where the resolvers are defined inline beside the schema definition. And we can define a custom resolver behavior at the same place. So perhaps our data model that's backing the product type gives us the full description automatically, and there's no reason why it wants to truncate it. But our client front end says, hey, we only need a subset of this content. It might be really long, so please give me a way to truncate my description. And we've decided to implement that at the edge of our system, being the resolver interface. Dynamic schemas are a complex beast where there's a lot of moving pieces, and it means many different things to different people. If we consider a multi-tenant system, there maybe needs to have different schemas customized for a different project or client. So when we think of generating schemas for metadata, I think of systems like Contentful or Hasura, where you're taking things like a database schema or JSON schema or domain-specific language or code reflection. These are all things that are helping inform the invocation of your runtime language to know what GraphQL types need to be defined based on this other context. When I think of code generation, I might also think of like a CLI toolchain or a core library, perhaps something like GraphQL Nexus, where the whole library's purpose is to provide a JavaScript declarative syntax that results in matching TypeScript definitions with the GraphQL definitions. Or you could also think of something along the lines of transformations. So maybe we're merging schema definitions together into one larger schema, or federation, where we're proxying some functionality to a subschema by wrapping it. With the CodeFirst approach, it is much easier to embed code generation logic right side by side with the type definitions. In this example, we're using GraphQL Ruby again, where we have the additional field named products now, which we want to return the product connection type. Instead of us having to manually write out the entire SDL for a product connection, product edge, we actually have some built-in code generators that can do it for us. In our case, the product type has the connection type built into it, provided out of the box by GraphQL Ruby, or we could actually write a custom class that also builds this kind of concept of a connection, or anything else, to be honest. We get things out of the box like arguments, types like product connection, product edge. And this is just all about being consistent, standard across the board, and minimizing what a developer has to write themselves. If we zoom in on the topic of schema transformations, we can come across the topic of schema visibility, where we might want to hide portions of a full schema for a variety of reasons. We may not want non-administrative users, so like regular users, to know about admin functions. Or maybe we have a new feature that's only available to a few users initially. We want to gradually roll it out. It's almost like a beta. So this is really important if we have one software system that's used by, say, internal developers and third-party developers looking to consume APIs. Maybe it's a public API. And in a schema-first approach, we would probably use the schema definition language and GraphQL directives to annotate attributes to describe the custom behavior. In this case, I'm introducing a custom runtime directive named Visibility that takes a single argument named schema, or indicating which schema this functionality should be exposed upon. The directive's implementation could access the request's execution context, and then in that context, we could check, does the current user or does the current API client have the necessary permissions to access the schema? And through that process, we can then determine, should that field actually be exposed as part of this available schema? In this case, the example is cost of goods manufactured. Do we want this perhaps field with internal business sensitive information publicly available, or do we want to keep that internally? When hidden, we should both hide this field through introspection, the SDL, and also just through query execution. So we could start out with this full schema that our server knows about, but then when we're running, we're going to essentially end up with an internal schema that has this cost of goods manufactured field on it. Or if we don't have the necessary permissions, we won't know that field exists because it won't show up through introspection, and I can't query it, and it should not show up in my error messages. If we were working in an environment where we had the full language runtime available to us, we could also take some alternative styles. So out of the box, GraphQL Java and GraphQL Ruby have a concept of visibility built into the library. No directives are necessary. By implementing the visible function, the server controls the ability to expose types, fields, arguments, enumerations, and more. When a type is hidden, any field that returns this type should transitively be hidden too. And that's basically schema trimming. We're not showing things that are partially invalid. We extend what it means to define a field in this code sample through the initialize function, where we're now accepting an optional custom parameter name schema. And then we're going to assign it into a class variable and hold on to its value for a later use in the visibility calculation. This is a naive example, but it's safer to default to keeping the content internal and using annotation specific types or fields before we make it public. So what I mean by that is just that this is an example, and we just say internal or public, but it'd be safer to default to hidden by default, and then only opt into exposing certain things when necessary. It's also critical to note that, again, visibility is not authorization. This is more just about hiding knowledge of a feature. Even if you've restricted the visibility of a type or field, you still need to set the appropriate API and user permissions. This same concept of hiding and showing schema members can be used to create a basic implementation of versioning. In the previous example, we could change the visible functions implementation to control what is defined in each version schema. So instead of something like internal and public, you can imagine version 1, version 2, version 3. Versioning is one way we could reconcile the expectations that published APIs are frozen, should never break, and that they're essentially forever. GraphQL takes a strong opinion on avoiding versioning to ensure compatibility with client expectations, where we are essentially only ever appending new functionality to our API, never removing or changing existing things. The @deprecated directive indicates that something should no longer be used, but unfortunately the specification doesn't really help us describe when that is going to be removed. There's no automatic or programmatic way to expose that functionality at this time. So the vast majority of changes are backwards compatible, but there may be occurrences where we need to pivot the trajectory of our API or feature due to new insights or past shortcomings, business requirements, or changing technology. Since this is GraphQL, we actually have the benefit of per field level granular analytics to help us understand who is using specific functions. So we can actually understand the impact of a proposed change. How many requests, how many apps, how many users would break if we ship this feature that changes from A to B in a breaking way. So tying this back to Shopify, at Shopify, we continue to learn lessons about commerce, entrepreneurship, society, and how they all interact with one another. Part of our mission is to make commerce better for everyone. And this includes the entire ecosystem of our merchants, their buyers, partners, and experts. We've been having a versionless REST API for close to 10 years, but in 2019, we decided to actually adopt a versioning strategy to establish clear expectations between the platform and the partners creating apps on it. I know we still have a lot to improve in our process and tooling, and we take breaking changes very seriously because we believe that each breaking change really subtracts away some trust from our brand and our system, and that our partners and merchants feel tangible pain when they have to deal with breaking changes. The process of making something better is continuous, and we need to keep this in mind with versioning. So every 3 months, we publish a new API version that contains the new, slightly improved API contract, which is valid for the next 12 months. Clients that have made a request to a version where it's no longer supported will receive a response by the oldest supported version, which is almost always still compatible, and thus not break the request. But this is imbalanced because we need to move the platform forward. Apps need time to adapt based on the platform changes, and then merchants rely on these apps to run their business. So we have to provide proactive, customized communication with our partners and merchants in advance of any breaking change based on their API usage. Through an analysis of GraphQL operations, we are enabled to do exactly that. We know who's using deprecated types, how often, and in what ways they might be using them. And in addition to that, we have an upcoming API release candidate version that allows anyone insider access visibility into what's coming into the next version before it's frozen and stable. APIs play a critical role in having an extensible system, making more things possible. And at the heart of a scalable, intuitive API is a great developer experience. And we're certainly striving to provide just that. As a commerce operating system, our merchants and partners expect stability, documentation, and evolution to support market opportunities. Our goal is to make all of this possible. Here in our diagram, we can see a brief summary of our versioning strategy. In the orange bar, we see the stable frozen versions that are available for 12 months. So in the case of something like in the case of January 2020, that version is actually available 3 months prior. It's actually available in October 2019. This gives someone a chance to try out a new feature. With versioning, as with anything else, there are trade-offs where things may not be quite ideal. With this approach to visibility as the way to implement versioning, we ultimately end up with one shared base schema across many versions. This is nice because it cuts down on code duplication and helps reduce overhead of maintaining multiple versions. But one of the biggest downsides we found so far is that the field and type name conflicts exist across versions because we have to have this one shared base schema across all versions. So this means we cannot actually change the return type or nullability of a field of a past version in a newer version. So we still unfortunately end up with some messy version suffixes like v2, v3, where things look out of place when only that field exists. If the cost of goods manufactured field was available for the versions 2019 all the way through to 2021, and then it goes away in the next version where the same field exists but with a different return type, it looks really weird to have a v2 but no v1. And the v2 suffix looks unnecessary because it's just superficial. So this isn't our ideal final state, but I think it's important to highlight that we have still reduced the user's cognitive load by trying to clean up our schemas. We're moving in the right direction. We're trying to use meaningful names, and we're removing deprecations on a predictable cadence, allowing our system to also continue to evolve on the back end and not have to carry the debt of past decisions forever. Today's code snippets are available on my GitHub repository. My team is growing, so if you want to work with GraphQL and make commerce better for everyone, you can try creating a Shopify app or come join me at Shopify. Thank you for your time today.